All right, so the question was, is time travel possible?
Mankind has always been fascinated by the thought of traveling in time. Over the centuries, there have been all kinds of ideas about how it could be done. But of course, time travel is impossible. Or is it? This is the story of Håkan Nordqvist, a man who claims to have visited the future.
Jag hade varit och jobbat på Öland. Och kom hem då och gick in i köket. Nej, vad fan. Det var precis som att man hade vatten på golvet där då. Jag tänkte, fan. Ja, det är något rör där under diskon och... Så jag hämtade verktygen då. Och in där och skulle börja dona och grejer och det och massa där. Och nå det, för det var så långt in när rören där då. Det var fan... Jag fick krypa in där och ja, bara kom längre och längre in där. Till slut i alla fall så blev det ljust och jag kunde ställa mig upp på det här. Jaha, och därför jag ser mig själv som äldre och kanske 70 och sånt där.
It would be very easy to dismiss Håkan Nordqvist as a liar, if it wasn't for this.
Det som tur var då, för jag tänkte det här kommer ingen tro på. Det finns inte en chans att folk kommer tro på det här. Så jag hade ju med mig mobilen så jag kunde filma det. Ja, vi stod där och tjafsade lite och... Ja, det var riktigt god känsla var det. Hur gott som helst.
Let's suppose for a moment that Håkan Nordqvist is telling the truth. If so, is there an explanation? We asked Hans Carlson, professor in theoretical physics.
Det finns en massa teorier om att resa i tiden. En sådan teori är tvillingparadoxen. Det finns teorier kring svarta hål. Det finns teorier kring maskhål. En genväg mellan två platser i universum. Enligt fysikens lagar skulle dessa teoretiskt kunna uppstå. Sannolikheten är visserligen inte särskilt stor, men de teoretiska förutsättningarna finns så att man kan inte avfärda det.
Nej, men jag vet ju bara att jag träffar mig själv i framtiden och att jag... Nej, men det här är jävligt gött. Sen får ju folk tro vad de vill.
Håkan Nordqvist stands by his claim, and scientists can't completely dismiss his story. Even so, the question remains, is this really possible? As Albert Einstein once said, the most beautiful thing we can experience is the mysterious. It's the source of all true science.
So the question is this possible? Rather than, is this real? Is time travel possible? It depends on three conditions. And satisfying those three conditions.
Imagine that we're able to control space, or control time. The kinds of things that we'd be able to do would be amazing. I might be able to go from here to here, to here, to here, and over to here in only an instant.
All right, so you can do that sort of stuff, obviously, by taking shortcuts through the space continuum. All right. So number one, the time needs to be a continuum, which it is. We know that. Number two, it needs to be curved so you can take shortcuts. If it's flat, forget it. That's not going to happen. And number three, the act of time travel needs to create its parallel histories. So those three conditions need to be satisfied. But here's the biggest question. Notice that every single possibility comes into existence and everything collapses into one single reality because in no universe you want to get a ticket. So if the universe splits into these parallel realities, and you know all these parallel realities are made up of the same atoms in the molecules, how come they remain invisible to us? I mean, there's certainly something there near absolute zero, but that's more of an interpretation. So why is it that the universes are made up of the same atoms and molecules, yet you cannot see them? So that's one explanation. We're not going to be able to, one question we won't be able to really answer satisfactorily.
Time travel can be complicated and complicating.
All right, we've seen this. So moving forward, three conditions. This is satisfied. Time is a continuum. So the past, the present, the past, all happen at the same time. All right. Space-time continuum needs to be curved. Is it? We'll find out shortly. Alternate timelines need to exist. Well, there is supporting evidence. All right, it happens near absolute zero. You got the Bose-Einstein condensate, and you have the Andrew Cleland's vibrating and non-vibrating paddle near absolute zero. So these are the things that they discovered as they're building these new quantum computers. And the quantum computer is based upon many worlds interpretation. Instead of using bits, they end up using qubits. It's ones, zeros, and ones and zeros. 1 and 0 is the many world interpretation that you're dealing with. So that's the reality. So the reality of many worlds interpretation is what the quantum computers are based upon. So the first condition is satisfied. There's some evidence for the third condition, but you can kind of say that there may be parallel universes.
But now, some scientists
So the question is the shape of the universe. Is it flat or is it curved?
have devised an experiment to calculate the overall shape of the universe.
If I send light rays through space and make a gigantic triangle,
All right, guys, the light is going to follow the curvature of the space-time continuum. If space bends, light is going to bend this way.
going from us here out to the farthest edges that we can see, and then back, the angles of that triangle should add up to exactly 180 degrees.
If the universe is curved like a balloon, the angles of the giant triangle would add up to more than 180 degrees.
If it's flat, 180 degrees. If it's not flat, more than 180 degrees.
To find out if the universe is flat or curved, they shot laser beams deep into space and made a giant light triangle.
Now we can tell, and the measurement is in, and the answer is it works beautifully.
Nice, so it works beautifully. So hopefully it's going to work for us.
Angles add up to exactly 180 degrees.
Oh, what does it mean? That means that the universe is,
That the universe is flat.
fuck, universe is flat, guys. All right, so this was, damn. All right, going into it, I figured that this was more science fiction than reality. I didn't want to teach a course like this initially, but this was an amazing learning experience because you do learn quite a bit about modern physics and how the universe came into being, this and that. So my conclusion was, no, time travel is not possible because the universe is flat. One of the art students evidently took an issue with that and then got in touch with the man himself, Kip Thorne. Remember, Kip Thorne is the guy who made this possible. Kip Thorne said, he said, well, he did not disagree with my conclusion. He thought that the time travel was still possible by creating artificial wormholes, time machines. All right, you can create a time machine today, and then from this point on, it allows you to be able to do time travel from the future to the past, for example. So he's the man himself. This guy, he's a Nobel Prize winner versus me, canon. Let's go with his interpretation. All right, this guy, Ernest Stripes. So Kip Thorne said, it is still possible. Artificial wormholes. Okay, so you can't really do time travel using black holes like the way you see it in the movies. You have to do your artificial wormhole and call it a time machine. So my initial indication was the space-time continuum is flat. So does this mean that no time travel? And that would have been my conclusion, except Kip Thorne thinks that it is still possible. You have to kind of create your own time machine for that to happen. So the question is, can you create your own time machine for that to happen? Okay, so we discussed that before. For you to be able to create a time machine, you have to create an artificial wormhole, which means that you need to have exotic matter, something that generates repulsive gravity, so that you can actually create yourself a time machine. So is there any way to generate exotic matter, some that has repulsive gravity, that could turn into a time machine? Something happened in 2013.
For Mashable, I'm Lauren Goris. Absolute zero sounds pretty final. It's as cold as something can possibly get. Negative 459.67 degrees Fahrenheit, 0 Kelvin. The point at which something is so cold that all of its molecular motion ceases. But physicists at Ludwig Maximilian University in Munich just froze something down to an even lower temperature. It relies on a quirk of quantum physics.
Ooh.
But for most...
So what does that mean? Guys, what happens to molecular motion near absolute zero? It slows down. At absolute zero, it completely stops. And these guys actually broke the third law of thermodynamics. They were able to get below absolute zero. So what happened? Matter started to behave in a strange sort of way. The gravity became repulsive immediately. All right, so it gives you repulsive gravity. This is known as dark energy. All of a sudden, it turns into the exotic matter that Kip Thorne was talking about in 1980s. With that in place, not only time travel becomes plausible, it also becomes possible at some point. All right, it's weird because going into it, I thought this was science fiction. Now I'm looking at it, all three conditions are kind of satisfied, so which means it's plausible. It's plausible. There's some evidence for the parallel universes. There's strong evidence. It's not proven, but there's strong evidence. Also, the matter, the particles, become repulsive, gravitational repulsive under absolute zero. So they behave like dark energy. So that's what you need in order to create a wormhole, and that becomes your time machine. All right, so scientific method is the way physics is done. All sciences are done. You need to have an observation leading to a theory. The theory needs to make predictions so you can test those predictions. So we kind of stuck to that as much as possible. And this was more of a plausibility argument. So the question is it possible? All three conditions are somewhat satisfied. So yes, it is plausible. So you cannot dismiss the possibility of time travel in the future, maybe a distant. We had some main characters here. All right, so we have to have a quick discussion regarding the main characters who played a major role. Regarding the time travel aspect of modern physics, this guy takes the center stage. So this is John Wheeler. John Wheeler happens to be an expert in Einstein's theory of gravity, and also he worked under Bohr. And notice that he's got his 2 PhD students. One of them is Kip Thorne, located right here, who won the Nobel Prize 2 years ago in physics. So Kip Thorne is the guy who said, oh, through wormholes, you may be able to do time travel. And then the second one is Hugh Everett, the guy who introduced the many-worlds interpretation of quantum theory into modern physics. So what's so weird about it is these are competing views. You got the many-worlds interpretation versus the Copenhagen interpretation. These are 2 major interpretations of quantum theory. All right, most physicists end up switching from Copenhagen interpretation to the many-worlds interpretation. All right, so this guy was working on his PhD under John Wheeler, and John Wheeler was going along with it for some time, and then, as you all know, Bohr had all of his troubles with Einstein. Einstein was dead set against the quantum Copenhagen interpretation, the probabilistic interpretation. So these guys have been battling it out up until literally both of them died. All right, this was something that, and then this new guy comes in. The year is 1954, and then John Wheeler is all excited. He's talking to Bohr. He says, hey, you're not going to believe this. I got this kid. He came up with a completely different version of quantum theory. He takes the observer out of the picture. He worked out the mathematics, blah, blah, blah. This kid is a genius, and now I want you to meet him. And Bohr didn't want to meet John Wheeler. Bohr was sick and tired of arguing with Einstein. And all of a sudden, you get this weird science fictional interpretation of many worlds, parallel universes. And he told Wheeler, just shut him down. He said, don't give him his PhD. This is complete nonsense. This is complete nonsense. He didn't want to deal with it. So John Wheeler goes to Hugh Everett. He says, hey, Bohr doesn't like your theory, so he wants you to alter it, or else we're not going to give you a PhD. And John Wheeler said, all right, anyway, so Hugh Everett says, hey, wait a minute. I'm not going to change it. That's number 1. And number 2, who's going to read it and believe in it? No one will, because it sounds very science fictional. Number 3, on mathematical grounds, the theory is solid. On philosophical grounds, it's solid. And number 4, he already had a job offer, which required a PhD. He was going to be working for the Defense Department. He said, just let me finish it up. All right, so no one will ever know anything about this paper. And John Wheeler goes, okay, if that's the case, it's a done deal. So as a result, Hugh Everett was allowed to finish up his PhD and publish it. And Hugh Everett was right for the most part. No one took it seriously. No one did for many years. Those of you guys who've seen the documentary will notice that. He eventually started to get the recognition that he deserved in 1970s. And by the time he was about to become a recognizable figure in physics, he had a heart attack and died. And then, so what happened over time, though? What happened over time is physicists went from Copenhagen interpretation to the many-worlds interpretation. All right. Both interpretations are based upon the probability waves. Everything is the same that the Max Born came up with. All right. So the question of what's collapsing, or the wave function. In the Copenhagen interpretation, the outside observer does. Outside observer does. In the many-worlds interpretation, no one does. The probability waves will collapse into every single possibility that it represents, creating all these many universes. So which interpretation is right, which interpretation is wrong? It's a personal choice, usually. What it is that you're comfortable with. All right. Copenhagen interpretation obviously works beautifully. Nuclear bombs, the atomic bomb, the electronics technology, all that stuff came out of it. Many-worlds interpretation is mathematically identical to the Copenhagen interpretation, except up-and-coming quantum computers. It's got variations, obviously. Up-and-coming quantum computers are based on it. So both interpretations work in the United States. In the United States, usually we don't really focus on the philosophy of these interpretations. That's not how physics is done. This is something that I would talk about to non-science students, because this is the sort of stuff that you guys usually eat up, and a lot of science fiction usually comes out of it. In the United States, the way the physics is done, this stuff is weird. This is weirder than science fiction. This is weirder than any religion that you can think of. But still, this shit is real. All right, this shit is real. In the United States, we say just shut up and calculate. It works. Mathematics works. It makes predictions, testable predictions, and the predictions usually come true. Not come true usually. It's 100% of the time the predictions are accurate. So that's the way it is done in the United States. Most physicists have a preference for the many-worlds interpretation, because the many-worlds interpretation does not require some kind of a godlike being collapse the waves into the universe that we live in. So that's the way it is done. Einstein's ideas are not dead in water. There is still evidence that we may be living in a universe which is static. Many-worlds interpretation works for the time travel purpose. Copenhagen interpretation does not work, because what you see is what you get in the Copenhagen interpretation. You cannot see the past, so the past doesn't exist. You cannot see the future does not exist, so you cannot do time travel in this universe. And in this universe, the gravity does not exist either, so it's not compatible with the theory of gravity. Einstein's universe, if you believe in psychic phenomena, deja vu events, you still believe in this universe. And the universe may still be a 4-dimensional movie. There's still the possibility. Gerard Hooft this guy's a 1999 Nobel Prize winner. He's still trying to revive the deterministic view of the universe. Hasn't succeeded yet. I don't know if he can succeed in something like this. This is the past history as far as I'm concerned. And again, just like everyone else, I got my own biases. All right, guys, so this is it. This concludes the course. So we're done with it. I'm losing my voice.